Hi and welcome into this video. We're going to cover a statistics problem as requested on Wyzant, and it's really focusing on finding the sample size. So we're going to read this and get into what is involved, what do we need to bring in, and how to set things up. Okay, it says that you're interested in estimating the mean weight of the local adult population of female white-tailed deer or doe. From past data, you found, the researcher, an estimation of the standard deviation, which turns out to be 20 pounds. What sample size would you need or in order to estimate the mean weight of all female white-tailed deer with a 97% confidence level within 9 pounds of the actual weight? So it seems like a lot, but we're going to really break this down. The first thing we always want to identify is what is the parameter? And it tells you straight off the bat, right off the bat, what that is, based on the fact that it says we want to estimate. So we're talking either point estimate or interval estimate. Specifically, it's going to be the interval confidence type of estimation, okay, of the mean weight of doe. So then we're given some pieces of information that's going to help us get to the answer. The first thing they tell us is that from a previous estimation of the standard deviation, it's 20 pounds. And then we're asked to find the sample size based on this confidence level. So the reason why I say it like that is because we are going to find the critical value, and in this case, we're going to use the Z distribution. That's going to relate to finding the sample size. And then it's also within 9 pounds. Always remember, whenever you see this keyword here within, that's going to mean margin of error. Okay, so all of this has to do with confidence interval, which is why I start off with the formula right here. There's usually two different ways you can see the formula written. You see it written like this as point estimate plus or minus the margin of error, which is the larger chunk of the formula. And that's your critical value times this fraction, which we would call the standard error, SE, which is simply the standard deviation divided by the square root of n, right? So this is in case of, sample estimates, sample or statistics, right, that we're dealing with, just going beyond looking at an individual data set. This is another way that we can look at it. This is in terms of our inequality as a basically showing the range. So the lower to the upper, okay? Now, we don't need to necessarily worry about the formula in its entirety. We're only focused on using the margin of error because all they want is the sample size, right? They just want to know what is the largest size that the sample could be in order to estimate with this type of confidence interval. That is the question. So we're going to just zero in on margin of error, just that part of the formula. And we can look at that as a separate thing. So I rewrite it as E, or you may see it in your book as, or class as MOE for margin of error. E is equal to the critical value times the standard error. Again, we're going to use the Z distribution, although we could use T, but that would kind of be, I don't know, it just would be counterproductive just because for T distribution, you have to know the sample size, right? In order to do find degrees of freedom, in order to find that critical value. So we have to use the Z distribution. That's the little tip here about this one, okay? So we're gonna go through that. And what I'm gonna show you real quick here is how you can go from the margin of error formula to the setup in the formula in order to actually solve for the sample size n. So you can just do a bit of algebra here. We start off by multiplying both sides by the reciprocal of the standard error. So you can see on the left side, multiplying with E, we have there the square root of n over the standard deviation rather than the other way around, because we want to get n outside of the denominator on top, right? And then isolated to basically be able to find n. So from that point on, we divide both sides by E, then multiply both sides by sigma or standard deviation. And finally, we're going to square root both sides. So that way we get rid of that radical over the n, kind of like freeing it, right? So we've totally isolated n on one side. And now it's set up equal to the sample size, which we're going to find. So the formula is the squaring of the critical value times the standard deviation over the margin of error. That is our formula. And you are welcome to write this somewhere in your notes. You may already have done that. You might already see that in your formula sheet if you have one for the class, because you may not necessarily need to do all this every time, right? So you can totally memorize it or write it down. So now we're getting into, given what we have there, we can finally set up to solve it, really set it up to solve it. So again, we're given the standard deviation is 20. Notice I wrote S. It could have came from a sample, some other sample, but we could also say that it may also be sigma. So we really don't know. So they're just saying standard deviation. But we're going to use that in place of sigma, 20 pounds. Our margin of error is 9. And then we're given the confidence level, but not the critical value, right? So here's our flow. This is how we're going to get to the critical value. We never ever really use the confidence level to actually directly get the critical value, whether that's z or t or even chi-square. We're always going to use something related to it. Okay, always remember that the critical level, confidence level and the significance level alpha are complementary to each other, which means just like going back to probability, you can add them up and they should equal 1. So these are two area values that are in a system together. And when you add them up, it equals the sum of 1. So I can take away the confidence level from 1 in order to get alpha, and then take half of alpha to get the critical value. Notice that the notation relates to the fact that we have to find alpha half, or that we specifically use alpha half to get the critical value. So there are some confidence levels that you can memorize its critical value for Z, right? But if there are those times where you don't have it memorized, this is the path, this is the flow to get to it. All right, so we're going to go through this now. So we're going to take the confidence level, subtract it from 1, and we get alpha here is 0.03. So on the flip side, we can say that the level of significance is 0.03. And then we're going to take half of that. Okay. And so this is going to be 0.015. This is the area that we use to find the z-score. Okay. So a lot of students are using charts in this sort of course. So we're going to just focus on that. But know that you can also use your calculator, and I'll make sure to write that out in the notes when we get back to our whiteboard. Okay, so in our Z chart, notice that we got 0.015. Now, you can kind of tell if you've practiced with the chart more that when you get a pretty small area, or if it's less than 0.5, right, to the left of the middle of the distribution, you're going to get a negative z-score. So always remember that the z-score for confidence level, we're always going to use the positive version, and it's really plus or minus of that z-score, because we're talking about, when we say in between, we're talking about two z-scores, two values, right? But we're always going to use the positive to get positive numbers. Okay, so we're just going to look for 0.0515, the area there. And it was nice to see that it was actually an identified value. It didn't fall between two areas. So then we're just going to track backwards. We're going to find our z-score here, and that is 2.17. Again, it's plus or minus 2.17, but we're going to use the positive version in our calculations for confidence level or interval. Always use the positive version of our critical values. Okay, so if you wanted to do this in the calculator, let's say you have a TI-84, I think it may also be similar for the TI-36. What you would do is you'll click on, not stat, you would click the second button, which is your shift key basically, and vars. Okay, and this is going to take you to the distribution menu. And then you're going to choose inverse norm, and you'll see that it'll ask you for the area, and it'll already have set up the mean and the standard deviation as 0 and 1, because that is the notation for a standard normal distribution. The mean is always 0 and the standard deviation is always 1 for a standard normal distribution or Z distribution. Okay, so we have our Z score, and now we can plug in everything into our formula. So we have 2.17 times 20 for the standard deviation over 9, and the whole thing is squared. Okay, so if you want to pause here, definitely do so. Try it on your calculator, or if you want to do it by hand, go ahead and calculate this for yourself. All right, and we're going to check back in now and see what we get. So when you calculate this, you should have gotten something like 23.2538, and I'm using my TI-84, so it has a pretty long list of digits. Okay, so in the case of sample size rounding, typically the rounding rule is you round up no matter the situation of the number, and you always want to round up to a whole number. So always, for the most part, always round up to the next whole number. And please follow the instructions that you have for whatever is your, homework system, homework assignment, because there may be specific instructions required. Just follow that on paper. However, you'll probably learn in statistics that for certain things, there are certain general rules for rounding, like for the mean and standard deviation. So for sample size, you will probably need to round up regardless. So even though it's 0.2, the number to the right of 3 is 2 and it's less than 5, you may think, oh, let's just keep it the same. Nope, we're going to round up. And my reasoning for this, in my opinion, or in my observation of understanding sample, is that you want to maximize, you want to exhaust as much room in the sample space as possible, because the larger the sample, typically the better in your, I would say, not just in analysis, but even before that, in capturing the data and being able to summarize the data. Okay, because it's all about being able to represent the population. So that's why they always emphasize that larger sample sizes are better. And that is it. That is how we set up and work through to answer this question. Please let us know if you have any other questions about this or anything else to do with statistics. And I wish you well in your learning endeavors.